Assalamu alaikum. My name is Ahmed Alhammadi and I'm a flight physics engineer here at LODD, working on the Hili aircraft. Hili is a hybrid electric VTOL aircraft, talking about the architecture of this aircraft. By going with a VTOL aircraft with a fixed wing, this means that we benefit from the superior takeoff and landing performance and the ability to operate in confined spaces like a rotorcraft, as well as having a fixed wing, which gives us superior operational capability during the cruise segment of the mission, allowing us to extend our range relative to a rotorcraft. When it comes to its hybrid electric propulsion system, we chose an electric propulsion system for the vertical segment of the mission, meaning that we can have a very rapid power output for vertical propulsion, quickly taking off and landing. Whereas for the horizontal propulsion of the mission, we have chosen an internal combustion engine, giving us long, sustained endurance and a long range in return. This gives us an advantage over fully electric aircraft because we are capable of flying for extended ranges. These decisions play a major role in the design of the external surface of the aircraft and its aerodynamics, or what we typically call the OML, the outer mold line. For example, as you can see, we have booms attached to this aircraft to carry the electric propulsion system. This is, of course, a major consideration when it comes to the design of the wing and its aerodynamics, as well as the other aerodynamic surfaces. This is a major point for us because now it means that we have to optimize the entire airframe to work as one unit, including the booms as well as the traditional aerodynamic surfaces of an aircraft. During the development of the Hili aircraft, we went through more than 25 different iterations. When we started, our tail assembly was actually a V-tail configuration, which is a tail that looks like a V shape mounted at the back of the aircraft. After performing many studies, we found that this tail may not be the best option for us for multiple reasons. One being that we have to couple our yaw and pitch motion, which is not ideal for our maneuverability. And the second point is this tail assembly typically is very heavy. Therefore, we decided to move away from the V-tail and change it to an H-tail configuration, which is what we see on the Hili today. This allowed us to first decouple the pitch and yaw motions, as well as reduce the overall weight of the tail assembly, giving us enhanced performance such as additional range and endurance. Now let's take a closer look at the boom specifically. There are two major design considerations here when it comes to the aerodynamics. The first is the cruise performance and the boom drag and how it influences the wing. And the second consideration is for the vertical propulsion segment of the mission, because the presence of the boom means that we will have an additional downforce or a drag caused by the vertical propulsion system pushing down the aircraft. These are two major considerations we must take into account when designing the boom. The boom on our Hili aircraft has been optimized to do both, meaning that we have minimum drag during the horizontal propulsion segment of the mission during cruise and transition, as well as reduced drag during the vertical propulsion segment of the mission, meaning that the wind created by the rotors do not push down on the aircraft as much.